let X be following a binomial distribution where the experiment will be repeated n time with probability P. The first thing is that P is between 0 and 1. And we're going to show that this function given by n choose k times p to the power k times 1 minus p to the power n minus k is a probability mass function of X. Okay, the key here is that we need to show two things. Is that Px of X is bigger than 0, and that the sum here of Px of X, or k, let's use k, where k is going from 0 to n, is equal to 1. Okay, so and after that we're going to compute the mean. Okay, we're also going to compute the mean for this probability mass function. So the first thing that we have is obvious, because here we have p is bigger than 0, 1 minus p is bigger than 0, and therefore this is just the product of numbers that are bigger than 0, and therefore px of small x is bigger than 0, or k is bigger than 0. We can also write this one as the probability that x equals k. Okay, here the second thing that we need to do is that we want to prove that the sum of the probabilities of all the k's where k goes from 0 to n is 1. Okay, to do so we have to write this one in this manner here. So this sum here, probability that x is equal to k, where k is going from 0 to n, is this sum, k going from 0 to n of n choose k, p to the power k times 1 minus p to the power n minus k, where k is going from 0 to n. Okay, here we don't need to do a lot of effort to see the result. Okay, we use the binomial theorem. Okay, now given any a and b, we have a plus b to the power n is the sum of n choose k, where k is going from 0 to n, times a to k, b to n minus k. Okay, here we're going to use a as p and b as 1 minus p. So doing so, here we have with a as p and b as 1 minus p. Okay, we have this expression here. Now on the left side we have p plus 1 minus p to the power n, which is 1 to the power n, which is 1. And therefore we have our result that we need. Okay, it's very clear. The use of the binomial theorem is critical here. You can show this result very quickly. Okay, so next we're going to compute the mean of this distribution here. So we know that the mean is defined as the sum of k times p when x is equal to k. K is going from 0 to n. Okay, the key is that here note that when k is 0, we have this expression is 0. That's why we start from 1. So k going from 1 to n of k times, I'm gonna change the probability mass function by its expression here. So it's gonna be p to the power, or n choose k, p to the power k, 1 minus p to n minus k. Okay, here there is this expression here, there is this term here, k times n minus k, p to the power k, 1 minus p to n minus k, where k is going from 1 to n. Here I made a video before about this expression here. Okay, so here we can prove, or I just proved that k times nk and choose k is the same as n minus 1 k minus 1. Okay, so I'm going to use that one here to help me. Okay, here I now have n minus 1 choose k minus 1 times p of k times 1 minus p to the power n minus k, where k is going from 1 to n. I can take the n outside because it doesn't change or doesn't depend on n. And I have n minus 1, k minus 1, p to the power k times 1 minus p to the power n minus k. Okay, here, this expression we have to be, okay, here I need to add one more thing. K is going from 1 to n. Okay, I can't change the index here. Okay, I can't change the index because I want to make it look like something that that's very easy to know. So therefore I'm going to use something else. Okay, I'm going to use this expression here. So now my expression of the mean is n, the sum, k going from 1 to n, and I have n minus 1 choose k minus 1, p to the power k times 1 minus p to the power n minus k. So I'm going to change, I'm going to use a change of index. There is another way to do this, but the change of index will help us. So if I let k minus 1 equals L, okay, here n is going to be the same. And here, when k is 1, L is going to be 0. When k is n, L is going to be n minus 1. N minus 1 is not going to change, but k minus 1 will be L. And here I have p to the power k. So k in this case is going to be L plus 1 times 1 minus p n minus k. K is going to be L plus 1. Okay, let me write this one more time and see what we're going to have. So L is going from 0 to n minus 1, n minus 1 L. Here, p to the power L plus 1 is p to the power L. I'm going to take this p outside. Okay? And here I have 1 minus p times this n minus L plus 1 is going to be n minus 1 minus L. Okay? So in this case, what we have is we have the binomial theorem applied between 0 and n minus 1. Okay? So remember the binomial theorem. So it's n choose k, a to the power k, b to the power n minus k. In our case here, we have just n minus 1. So here I have n minus 1. And k is going from 0 to n. Here, if it's going from 0 to n minus 1, okay, I'm going to always have this minus 1 here. Okay? So this one is np, okay? And I have p plus 1 minus p to the power n minus 1, which is np times 1 to the power n minus 1, which is 1. Therefore, I have np. This means that the mean here of our x is just np. Okay? So the mean of a binomial random variable is n times p. Okay? We have done all the steps very easily so you can follow them. The key is that you need to know the binomial distribution and you change these indices correctly. Okay, if you see any errors or mistakes, please let us know. Please like, share, and subscribe. Thank you very much.